So my name is Brennan. I'm the Chief Protocol Engineer at Syndica. And today we're going to be giving a talk about building SIG, a read-optimized validator client. So who are we? We're Syndica. We're a Web3 native cloud. We specialize in RPC infrastructure, as well as developer tooling for the Solana ecosystem. So in our V2, we have things coming up like Elastic nodes that scale depending on your RPC requirements, as well as Chain Stream API, where you can actually stream accounts and transactions directly from the validator. And we also have app deployments, where you can deploy your front-end application on our platform and have everything all in one place. So with all these features, we've had to run a lot of the RPC nodes ourselves, and we noticed a problem. The problem was that 96% of calls made to nodes are reads, but Solana is currently plagued by slot lag. And so more specifically, we found that RPC validators were falling behind the head of the node. So we have two charts here. One shows the slot lag on Ethereum, and one shows the slot lag on Solana. And so we measured across 9 different providers over a 90-day period. And you can kind of see the darker the color, the more that these validators are lagging behind the head of the network. And so you can see in Ethereum, there's not much color. Slot lag really isn't a problem. But in Solana, there's a lot of color, and slot lag is an enormous problem. And so we dove into the data to figure out what was causing this slot lag. And we found that there were specific RPC methods that were the culprits. So we have another figure where on the x-axis, we have the frequency of these methods being called. And on the y-axis, we have the maximum reads per second that these methods can achieve. And so you can see there are specific methods that are both low in the reads per second that they can achieve, as well as high in the frequency of them being called. Right? So these are the methods that we really want to fix, and these are the problems. So that's why we're building SIG. We're building SIG in the open source for the whole community to learn from. We're releasing blog posts, videos, explainers, everything to make it easy to basically run these validator clients yourselves. And so to go over the goals of why we're building SIG more specifically, one of them is reads per second. So this is fixing the slot lag problem that we were talking about before, and just optimizing it for reads. We also want to improve the client diversity, so introducing another client onto the Solana ecosystem should improve the fault tolerance of the network. And also protocol accessibility. So we want more core contributors to come and contribute to the core base. And so we're releasing blog posts, documentation. We're making the code very readable to make it more accessible. And now I'll pass it over to Drew to talk about why we chose Zig as the programming language.
Hey everyone, my name is Drew. I'm a senior protocol engineer at Syndica. And yeah, I'm going to tell you about why we chose to implement the SIG validator in the Zig programming language. So the two main reasons are performance and readability to accomplish the goals that Brennan just laid out. So Solana needs to process a lot of data. It's read and write intensive, and as Brennan pointed out, RPC nodes are struggling to keep up. So we need a solution to improve the performance. So Zig is a great tool for performance optimization, and that's why we chose it. In order to optimize performance, you need to be able to manually control the way that memory is managed. And basically what that means is that anytime a computer program needs to process large amounts of data, it needs to make a request to the operating system to ask for an allocation of memory. And if this is not managed correctly, it can lead to significant slowdowns in the program. So the problem with almost every programming language is that it does implicit memory allocations behind the scenes, and the programmer doesn't really have a lot of control over this. With Zig, there are no hidden memory allocations. That gives a programmer the ability to directly customize all of this behavior, which gives unparalleled control over memory and performance in Zig. Another great advantage of Zig is its C interoperability. So Zig itself is a C compiler, and it makes it extremely easy to run C code from within a Zig program, as you can see in the code example here. And another great thing about Zig is the SIMD support with the built-in vector type, which allows us to take advantage of a lot of CPU performance optimization features. Another reason why we are using Zig is because it is very readable. So readability is a huge goal for us, and if you look at like the Solana Rust code base, it is very complex and can be difficult to understand. So our goal with Zig is to have it be easy to understand, so it's easy for people to contribute, and with more contributors, we can build more high-quality software. So Zig is simple, it's transparent, and it's easy to learn. It has simple syntax, which means you can express powerful abstractions with ordinary Zig code, and it's transparent, so there's no hidden control flow. That means is that if there's any kind of like resource cleanup or memory allocations that's explicitly laid out in the code, and you don't have to dig through layers and layers of code. It's all right in front of you to understand. So because of this, it's easy to learn, and it's easy for newcomers to contribute. So I'll pass it back to Brennan.
Yeah, so what's the progress on the SIG project? So we completed Gossip. This is all about peer-to-peer communication as the entry point into the network. We basically finished AccountsDB. This is all about representing the state of the network and the actual accounts. We're currently working on the repair stage. This is all about fetching blocks from the current state and catching up to the network. We're also working on the SVM. This is Solana's virtual machine, all about processing transactions and getting to the next state. In the future, we're planning to work on consensus, Tower BFT. It's all about processing votes and forks, et cetera. We're going to be working on the RPC, which is all reading the data that we just stored. And then it moves more into the leader production, block propagation, and those are the things we're going to be working on. Now, we'll be moving more into some technical details of some interesting things that we came across while building SIG. So specifically with AccountsDB, to give some background, there's these things called snapshots. It basically represents the entire network in a single slot. And there's two main components in these snapshots. One is the metadata, which contains useful information about the snapshot. But also there's account files. And these actually store the bytes of the accounts that live on chain. And so one of the important things is that when you're starting up a validator, you need to build a map from a certain public key or an address to where the actual account lives in these account files. And so you can think of it like a hash map. You basically have a pub key, and you map it to where the file is and where that account lives within that file, or the offset. And so while we're building this account index, there's a couple interesting things or problems that we came across. One of them is with fast reads and fast writes. So when we're initially starting up the validator, we want to be able to generate this index extremely fast to catch up to the rest of the network. And we found that the standard library hash map just wasn't fast enough. So we had to implement our own hash map from the ground up in Zig and base it off Google's Swiss map. And so there's some couple interesting features that we came across. Pack structs is one of them, where it gives you a transparent understanding of the memory underneath the struct. We use SIMD operations for fast equality indexing. It feels like native Zig, you can see in the code. And we got 2x faster writes versus standard library, which was a massive accomplishment. We also, another problem that we came across was that when you're generating this index, because there's so many accounts on Solana, the validator was actually running out of RAM and was not able to start. So we had to figure out a solution to this. The solution was to move the index onto disk memory. And so Zig made this really easy to do because it has an allocator interface. And so all we had to do was create a new disk-based allocator that implemented this interface, give it to the structure, and everything worked just as expected. And so there was no code changes. We got a massive improvement really easily. So now I'll pass it to Drew to talk a little bit about repair stage.
Thanks, Brennan. So the next thing that we're working on is repair. So what is repair, and why are we working on that now? So basically, we've loaded every account from the snapshot into AccountsDB, and it works great. But the only issue is that the snapshot represents a moment in time, which is in the past. And a validator needs to know the current state at every point in time. So in order to do that, you need to process every block that has occurred since the snapshot was produced. And the repair service is in charge of ensuring that we receive all of those blocks. So I'll take a second just to introduce Turbine. So Turbine is the mechanism that validators use to share the latest blocks with each other. The basic idea is that you have one validator is considered the leader, and that leader creates a block. And a block is basically just a big chunk of data. And then it breaks that chunk of data up into smaller pieces called shreds, and it distributes those shreds out to some of the highest stake nodes, and then those nodes send it out to other nodes, and so on until every validator has received every shred. One thing to note about Turbine is that it's only doing this with recent blocks that were just generated, not just all blocks through history at all times. And there's also the possibility that some nodes might not receive every single shred due to network issues. So on this slide, we have a diagram that represents 3 blocks for 3 slots. And you'll see that the first one is complete. That's what all the green means, whereas the next 2 have some shreds that have not been received. So repair is the service that goes through the block store, constantly looks at all the blocks, and it understands which shreds are missing, and then it sends out the requests to other validators to send over those shreds. And so this is critical for after we receive the snapshot, and there's many, many slots for which we don't have any shreds from the block at all. So when nodes respond, we can process those shreds, rebuild the blocks, and update accounts DB with the latest state. So now I can go into a little bit of details about the architecture of receiving and repairing shreds. So I'm going to be using terminology that we've been using in the SIG validator, but you can also see some of the Agave terminology there written in gray. So this basically represents a single validator, but you also see to the left there's an orange box that represents upstream validators that are sending us shreds. So the section highlighted in blue represents the shred collector, which is the portion of the validator that is collecting and managing the incoming shreds. So the shred collector is then broken up into 4 components. The first component that receives the shreds is the shred receiver. And that one is responsible for listening to data from the network, doing some basic checks on that data to make sure that they're well-formed shreds, and also communicating with other validators to let them know that we're alive and able to receive data. Then the shred verifier takes over, and it verifies the signature on those threads in order to make sure that it was actually the leader who created those shreds and not some malicious actor. After that, the shred processor takes over, and it loads those shreds into the block store. And it also submits it to the retransmit stage to get sent to other validators over Turbine. So while all this is going on, the repair service is constantly monitoring the block store and identifying which shreds are missing. And then it sends requests to the upstream validators. And then when those validators respond, it all follows that same path that I just described. So you might be wondering, does this work? Can I run this right now? And the answer is yes. You can run SIG from our GitHub repo, and it'll run our initial implementation of the shred collector by default. It'll just automatically run it. So you just run the SIG validator command, and you just need to pass an entry point to indicate like which cluster you want to connect to, devnet, mainnet, whatever. And there's also an option where you can specify a slot number. This is just a temporary option where you can say, I want to repair from a certain slot, and it's going to prove that it can repair from any point in time. So when you look at the logs, you're going to see the initial thing is catching up. It's going to be processing like massive numbers of slots. And then after it catches up, it's going to be log messages indicating that it's processing about 2 slots every second. So that's it for repair. We're going to continue improving the shred collector as we implement the block store, which is our next step. And so yeah, everything is being developed in open source on GitHub, where you can track our progress and you can contribute to our project. We're very open to contributors. And we're also very excited to share all of our progress with you guys. So, through talks like this, as well as through blog posts. So we have a blog on the Syndica website where we have these deep dive blog posts that describe everything that we've learned about the inner workings of Solana, as well as some updates on our progress. So our goal with the SIG project is really to advance the ecosystem as a whole and to solve some really big problems. And the best way to do that is as a community. So we really hope that you guys will join us. So I hope you guys enjoy the rest of the conference, and thank you so much for your time.